Okay, here on example 2, we want to try to solve a logarithmic equation by using exponential form. So this is our logarithm equation that we're going to try to solve. Um, Here the example is the amount of energy, E, in ergs that is released, so this is our unit, ergs, that is released by an earthquake is related to its Richter scale magnitude, M, by the equation log E equals 11.8 plus 1.5 M. So if you ever hear, like, in San Francisco, there was a 7.4 magnitude earthquake, or in Haiti, there was a 8.1 magnitude earthquake. That's the magnitude that they're referring to. Although the scale was created in the 1930s, earthquakes that occurred before its invention have been estimated using the Richter scale. For example, an earthquake in Cyprus in 1222 is estimated to have measured a 7 on the Richter scale. How much energy was released by that earthquake? Okay, so this is kind of getting at a common use of logarithms. So before we get right into the equation, let's kind of talk about why they gave this example. Logarithms are often used in situations where you've got a really, really broad range of data and you want to kind of compact it onto a graph that makes a little more sense. So, like, when you have exponential graphs like this, you can see that they shoot up really, really fast. And in order to show more than, like, 1, 2, 3 data points, you basically just get like a line that goes straight up, and it's really hard to, like, get any good intuition on what you're looking at when 10 to the x, 8 to the x, 4 to the x, they're all basically just going to look like this. They're all going to just kind of shoot straight up after a few x values. So if you have something like earthquakes, which can go from very, very small numbers to very, very large numbers, it's better to have a different kind of scale on your y-axis. And the scale that we usually use kind of will look something like this. It'll be like 10 to different powers. So 10 to the second, third, fourth, fifth, sixth, seventh, eighth, ninth. Those values are representing, numbers like this. So, for example, if we don't do earthquakes, we look at internet hosts. So this is saying, like, how many websites were there? How many different website hosts were there? Well, early on, there were only slightly more than 100, maybe 400 or 500. But then by 2010, 30 years later, we're up to billions of internet hosts. Now, if we're going to write that on a normal scale, just 1, 2, 3, 4, 5, 6, we wouldn't be able to represent all this data because we'd have to have a y-axis that went up to a billion, and our graph would be, billions of times taller than this. Um, what we do instead is we kind of compact all the data, and we say that for every interval on the y-axis, for every kind of like row here, we're getting 10 times bigger. So this is what would be thought of as a logarithmic scale, where we get 10 times bigger as we go along. That's what the Richter scale is showing. So they're saying that there's a big range of different earthquakes that can happen. You can be up to a 10 to the ninth. You can be down at 10 to the negative first. You can be anywhere in between. But since that's such a large range, we're going to use this kind of logarithmic scale where every time we move up a certain distance, we're actually getting 10 times stronger, right? We're not getting just a little bit more strong, we're getting 10 times stronger. So a magnitude 4 and a magnitude 5 are 10 times different. 5 is 10 times bigger than 4. A 6 magnitude is 10 times bigger than 5. A 7 magnitude is 100 times bigger than 5. An 8 magnitude is 1,000 times bigger than 5. Okay, so this is one of the most common uses for these kind of like logarithmic number systems, is that we will be using them to express descriptions of things that span very large values that we want to kind of compress and look at on a smaller graphical scale. Okay, so if we have this equation, log of E, so log of the energy equals 11.8 plus 1.5 times the magnitude on the Richter scale. Okay, so they said the magnitude was measured to be a 7. So we can go through that and we just say, well, we're going to continue downwards. We're going to say log of E is going to be equal to 11.8 plus 1.5 times 7. 1.5 times 7, well, that'd be like 7 and 3.5, so 10.5. Together, these would make 22.3. Okay, so keeping in mind, we're looking at a common log right here. So that's log base 10. And this is saying that E, right, how would we rewrite this if we were just going to rewrite it as an exponential equation? This would be saying that 10 to the 22.3 is equal to E, right? This number raised to this power gives us that end product. Okay, and at this stage, we just take that right into a calculator. Okay, we're not going to do that one by hand. We're just going to take that into a calculator. And when we do 10 to the 22.3, gives us 2 times 10 to the 22nd ergs of energy. And that is how we would work through a problem like that.